So, hello everyone. I am Aadarsh Pathak. I am a second year PhD student, again working with Stuart. So today I'm going to discuss about my project which I have been doing last year, particularly focusing on an analytic model to make predictions for emission line galaxy properties, especially for the high redshifts. Okay. So what are these emission line galaxies? It's simple, right? The galaxies showing emission lines are emission line galaxies. So we have a galaxy, we have stars surrounding by the gas component or dust. This gas component can undergo collisional excitations or radiative transfer, and in this form they emit emission lines. And we have actually observed this in the form of the spectrum. These lines are important because it inherits important properties of the gas, so it can inform you about the number density, ionization parameter, pressure, and many more. So okay, so this is the emission lines, and where I'm looking at? So I'm looking at the epoch of reionization. There has already been two talks on that. So this is the regime where the neutralizium transforms into an ionized one. And if we are looking at these high redshift galaxies, we have a very limited physical information about that. This is because before JWST, we were mostly relied on photometric data, which are highly being contaminated by the rest frame optical emission lines, which somehow puts uncertainties in determining the stellar masses and other stuff. But thanks to JWST, now the things will be sorted out. If we talk about the epoch of reionization, one of the JWST survey which is going to focus on this regime is the FRESCO survey. So it's a survey which is going to focus on 4 to 5 microspectrum in its every field of view. So it will cover 260 arc-minute square field in the deep candles deep field. However, it is going to cover a redshift range of 1 to 9, but in my analysis, I'm mostly focusing on the redshift ranging from 7 to 9, shown in the green line here. So as you can see, the most prominent emission line which we're going to observe here is the doubly ionized oxygen and H beta line. So these were the things which motivated us to move forward. So what we thought, we started to think of a model, analytic model, which can incorporate the physical properties of these galaxies. So these were the basic key steps. So we just picked up a simple analytic model, like a star formation rate density model, putting some ingredients in that in the form of various physical properties. Then we calculate the possible line luminosity or flux for the desired emission line, which is going to be observed through JWST FRESCO. And then finally, we made predictions that what's going to be the number of galaxies we're going to observe. Okay, so the first step was to include the star formation rate density model. So I picked up a model which was originally proposed by Vaidi and Loeb in 2012. So it just includes a galactic disk vertically supported by hydrostatic equilibrium. It undergoes major merger, and after each major merger, the starburst is basically being triggered, which lasts for a certain period of time. The model also includes a supernova feedback effect, which was originally proposed by Clark and Oy. So it assumes a super bubble formed by a certain number of supernovae, which has some radius. And we compare this radius with the scale height of the disk in order to infer what fraction of supernova energy is going to be used up as their feedback energy. So these two feedbacks, FSN or FD or FT, depending upon the comparison, it is incorporated in the star formation efficiency of the model, which is again used to calculate the star formation rate and hence the star formation rate density function. So here on the left-hand side of right-hand side of the plot, I'm showing you the how many galaxies we are going to observe per megaparsec. That's what the star formation rate density function is. So it matches quite well with the observation here. So we move to the next step, that means extending the model. So motivated by the lines which we are going to observe in the JWST, we have particularly focused on the two physical parameters, although the model in itself calculates other physical properties. So first quantity which we evaluated is the ionization parameter. So in a very simple sense, it just gives information about how the ionizing source and ionizing gas is being interacted. So it gives you ionization information about the ionization state of the isomer. By formula, it just simply gives you the it is just the ratio of the amount of flux with respect to the number density of particles. So here in the equation, Q star is basically the ionizing photon luminosity represented as a photon per second, so which we have derived from the super bubble, which I was discussing earlier. NP is basically the number density of particle, which goes like this. So it evolves with the halo mass, and it also evolves with the redshift as but if we focus on a particular halo mass. Now, keeping this in mind, we have now here I'm showing you the ionization parameter plot with respect to the star formation rate. So here again, we can see that the ionization parameter is evolving with the star formation rate. And for if we talk about a particular star formation rate, then we are going to see the high ionization parameter for high rates of galaxies, which is quite obvious and mentioned in many of the literature. But we still believe that for high star formation rates, such a high ionization parameter may not be physical. So we are planning to implement the effect of turbulence in our later paper or in our later work. But for instance, if we include a turbulent velocity in our number density model or simply in our Shafadi model, we can see that the ionization parameter is lowered a little bit. So which is a good sign to move forward ahead a little after. The second physical quantity which we evaluated is the galactic chemical evolution. So we just included a closed box model, no inflow or no outflow of gas, just the gas presenting inside the disk. So it is just depending upon the how much gas is present at any time with respect to the how much gas we had initially. So if you can look at here, depending upon the disk mass and the stellar mass. So this stellar mass is again dependent upon the star formation efficiency, which goes like this. So in the for the low star formation rate, you can see the lower star formation efficiency, which shows that it has a supernova feedback effect on the low mass galaxy. So if we plot the gas phase metallicity here, we can see a similar kind of trend as we are seeing in the star formation efficiency. So these were the two main physical quantities which were required to calculate the main emission line, which is the W ionized oxygen. So on the left hand side of the plot, I'm showing you the W ionized oxygen, the first 5 ground level of the W ionized oxygen, and the line which I'm going to observe here is shown in the red square, which is the 5008.2 angstrom. So this is the formula for that. We can see here there are basically two variables. First one is the gas phase metallicity, which I discussed earlier, and second one is just the ionizing photon luminosity, which I'm showing here with respect to the stellar mass. Rest of the things are just the coefficients. So here I'm showing you the plot, how does the line luminosity evolves with the star formation rate. So we can see clearly that it is evolving, but it is not quite evolving with the rate space. And since this line luminosity is being derived from the star formation rate and ionization parameter is also dependent on that in our model, we can somehow correlate these two quantities. One can also look at the line ratios of O3 and beta as they are the good diagnostics of the ionization parameter and metallicity. However, we are still searching for a better calibration. So with the existing calibration, I tried to calculate the line ratio with respect to the LO. Here I am showing you the evolution of line ratio with respect to the LO3. You can see that it evolves. So if you are going from lower luminosity to higher luminosity, the ionization parameter is increasing and metallicity is decreasing. So these were the few ingredients, and with that, finally, we tried to calculate that, okay, so these are the line luminosities we have. These are all the ingredients. So how many galaxies which we are going to observe for a particular megaparsec? That means the luminosity function. So here I'm showing you the luminosity function for that for a particular line luminosities. And you can see that it is matching quite well with the latest observations of JWST. So it finally motivates us to go forward and look at how many galaxies we are going to observe for the JWST FLESCO survey at redshift 7 to 9 for the given area and for the given flux limit. And we believe that it is going to be 330 to 350 galaxies. We will see. That's all. With this, I can conclude my talk. So we basically used a star formation rate density model to incorporate the facts of various physical properties, and then we used this model further to calculate line luminosities of W ionized oxygen and also find the luminosity function for the following luminosity. That's all. Thank you.